Hello everyone and welcome to lecture material for week 6. In this lecture we will talk about different applications of heat transfer. So by the end of this lecture you should be able to understand what is an insulation and how we can design an insulation system and what is the critical thickness of insulation. We will also look another application that is heat transfer in transient heating and cooling systems. And finally, we will look at a third application that is heat exchangers and their classification. Okay, so let's look at the insulation case. So heat transfer is an important subject, and actually it's one of the most important subjects that you will learn as a chemical engineer, because heat transfer is everywhere in our daily life but also in industry. Okay, so whatever industry you go, you can always find some basic applications of heat transfer. But another important point about heat transfer is that heat transfer is one of the three main conservation phenomena that you deal as chemical engineers. So one is momentum transfer, the mass transfer, and heat transfer. Okay, so if you understand the concepts of heat transfer, not only you can understand many processing situations, but you can also understand these other conservation phenomena, because they more or less follow the same basic principles. Okay, so as I said, that heat transfer has several applications and they are present everywhere. So one of the most common example is heat exchangers. So any industry that you visit, can always find some heat exchangers. The second most common application is insulation, because we always want to conserve the heat in the system. So we always try to use insulation so that we don't have heat loss to the environment. Some other examples of heat transfer are heat dissipation and thermal energy storage. Okay, so let's look at the application of insulation. And so here we are going to look at heat loss through a composite cylinder. Okay, and the reason we are looking at cylinder is because a lot of the systems in any process engineering plant, they can be approximated as cylinders. Okay, so we have cylindrical vessels, we have all the piping in the process plant that can be approximated as cylinders. So we are going to look at how the heat loss happens through a composite cylinder. Okay, so for example, you have a pipe, and in that pipe the heat is flowing, and so like, let's say this is the pipe and the hot fluid is flowing through it. We want to put layers of insulation around this pipe. Okay, as you can see here, so you have, let's say this white is one layer, then you have second layer, and then you have another material third layer. So we want to see that how the heat loss happen through this composite layers. Okay, so for example, we can look at different cylindrical layers in series. Okay, so the easiest way to do it is to use the concept of thermal resistance and its analogy with Ohm's law that comes from electricity, for example. So let's say you have a process plant where you have a pipe that is non-insulated, so the pipe is without any insulation, and you have a fluid that is moving in the pipe at temperature Ti, for example. Okay, so this is the system, and then outside the pipe you have, let's say there is a lot of wind, so it's a windy day, so the wind is blowing outside. So what kind of heat transfer mechanisms are involved here? So there are three basic phenomena. First one is because the fluid is moving inside the pipe, and it means that because of the motion of the molecules you have some form of heat transfer. So you have the convective heat transfer, and that is represented by here Hi, that is the internal heat transfer coefficient due to convection. Then the heat passes through the wall. Okay, so that is the solid pipe wall, and the heat is transferring through it due to conduction. And then we have the third mechanism that is happening outside the pipe. As I said, that it's a windy day, for example, so the heat is being conducted from the pipe surface to the environment. Okay, so we have again another form of convection outside the pipe. Okay, so now in order to calculate what is the net heat transfer, we can use the analogy, as I said, from electricity, like Ohm's law. So if we use that concept, so we can say that the net heat transfer is related with the driving force, that is delta T, through the resistance. Okay, so we have, let's say we have R1, R2, and R 3 here, okay, because we have 3 resistances. So if these resistances are in series, we know from electrical analogy that we can actually sum these resistances to give us the total resistance, okay. So we know that we have the resistance due to convection, that is 1 over AHI. A is the surface area, HI is the heat transfer coefficient. For conduction, we have X, that is the thickness of the wall, divided by the surface area times the conductivity of the system, thermal conductivity of the system, and then again we have the convection outside the wall. So if you sum all these 3 resistances, because they are in series, so we can sum them up to get the overall resistance. Okay, so to calculate the net heat transfer, we need to calculate the resistance of this composite system, that is different layers of the system. Now let's look a situation where now the pipe is insulated. Okay, so again we have some fluid that is moving inside the pipe. So the pipe is here, and then this is the insulation layer, and that is the pipe. Okay, inside the pipe we have a fluid that is moving at a temperature of TA. Okay, so we have the first resistance that is due to convection inside the fluid, and that is represented by RA. Then we have the second resistance due to the wall of the pipe, as we saw in the previous slide as well, due to the conduction resistance, that is R1. And then we have another conduction resistance due to the solid insulation, and that is represented by R2. And the pipe wall has a conductivity lambda1, and the insulation layer has a thermal conductivity of lambda2. Okay, and at the outside of the wall you have the heat is being transferred to the environment, and that is due to convection. So we have RB as the second convective resistance. Okay, so in order for the heat transfer to happen, so if TA is not equal to TB, it means that the heat is going to transfer from the and TA, if it is larger than TB, then the heat is going to lose from the system, going from the fluid to the environment. So we can calculate what is the net heat transfer if we have the driving force, that is TA minus TB, over R, that is the total resistance. Okay, so the sum of all these 4 resistances, because they are in series, gives us the total resistance of this system. Okay, so let's see if we can actually expand these different resistances from the knowledge that we already learned from these lectures. For the case of convective heat transfer, we know that there is the resistance inside the system, that is due to the and this resistance is equal to 1 over HA, that you previously learned in the lectures of convection. Now we have 2 convection processes happening in the system, that is, one is inside the fluid, that is inside the pipe, and then the second that is outside the pipe due to the loss of heat to the environment. Okay, so if you write down again this is a 3D system. Okay, so because it's a pipe, so we also have the length of the pipe, that is H in this case. So if we use that, we know that the surface area, so this is, let's say, AS, so the surface area of the pipe is equal to the length of the pipe times 2 pi r. Okay, and then based on that we can write using this equation here, we can write RA, that is the resistance in the inside of the pipe due to the convective resistance. We have 1 over HA 2 pi r naught, that is the inside radius of the pipe, times H. And similarly we can write the resistance of the outer fluid, that is RB, that is 1 over HB times 2 pi r2, that is the total radius of this pipe to the surface of the insulation, and from where the outside for example layer starts, and then H, that is the height of the the length of the pipe. Okay, so we know what are the convective resistances of this system. Now let's look at the conductive resistances. So we know that from the previous lectures, we know that the conductive resistance of a cylindrical wall can be written as R natural log of the outer radius divided by the inner radius divided by 2 pi h lambda, that is the thermal conductivity of the wall. So if we use this generalized equation, we can write the R1, that is the resistance due to the pipe wall, and R2, that is the resistance due to the insulation wall. And here if you see that we are using the respective radiuses, so for case of R1 we are using R1 over R naught, while for the case of R2 we are using the outer radius of the insulation divided by the inner radius of the insulation. Okay, so lambda 1 is the conductivity of the pipe, and lambda 2 is the conductivity of the insulation. So we know all these values of resistances now, so we can use this equation that we previously discussed, and if you put all the values of resistances in this equation and get the total resistance, we can calculate what is the net rate of heat transfer in this system. Okay, so this is one mechanism of looking at how we can actually use these resistances to calculate the net heat transfer through the system. Okay, so that is all for this part. Thank you for your time.